We are jumping straight into it today with a really interesting paper from ByteDance Seed called GRRL, going dexterous and precise for long horizon robotic manipulation.
And this one is, it's super practical. It's basically a blueprint for taking these big generalist robot models we're all seeing.
The ones that can do a bit of everything.
Exactly. And turn them to reliable specialists for things that, actually matter in the real world.
Right, and the core idea here is surprisingly simple, but I think really critical. These big vision language action policies, or VLAs, they struggle with precise tasks because they make a faulty assumption.
They assume the human demonstration data they're trained on is perfect, that it's optimal.
Which it just isn't, especially for something super dexterous like lacing a shoe, which is the big task in this paper. Human data is full of noise, hesitation, little mistakes.
Absolutely. So GRRL tackles this head-on with this really sharp three-stage pipeline. First, they use reinforcement learning to filter out all that bad, suboptimal data. Then, they augment the clean data using a clever symmetry trick. And finally, they use online RL to reinforce the policy, basically aligning how it trains with how it's actually deployed.
And the result, it really speaks for itself. They hit an 83.3% success rate on autonomously lacing a shoe through multiple eyelets.
A task that was, for all intents and purposes, unsolved by learning-based methods before this.
Yeah, this really feels like the difference between a cool lab demo and something you could actually, deploy.
It's a big step towards making these generalist policies trustworthy when precision is not negotiable.
Okay, so let's unpack this properly. Let's start at the beginning. We've all been seeing these amazing generalist models like GR3 that have this incredible breadth. But like you said, when the rubber meets the road, or maybe the lace meets the eyelet here, they just fail.
They do.
So what are the core bottlenecks that GRL is trying to fix?
You could really break it down into 4 specific problems. The first one is the obvious one, which is just the physics of it.
Right.
Dexterity with precision.
Right.
You need millimeter-level control, and you're working with deformable objects like a shoelace. It's a really, really unstable control problem.
And it's not like you're just picking something up once.
Exactly, which is problem number 2. Long horizon robustness. Lacing a shoe is dozens of steps, and any tiny error at the beginning,
it just gets bigger and bigger.
It compounds. A tiny mistake on the first eyelet means you have a catastrophic failure by the time you're trying to thread the 4th one.
And these models are trained with behavior cloning. So we have to talk about the data itself.
Which brings us to the third, and I'd argue maybe the most damaging bottleneck, the suboptimal human demonstrations.
The messy data.
The really messy data. When a human teleoperator does this, they hesitate, they kind of wiggle the gripper to get a better angle, they make tiny corrections. If your policy just blindly clones all of that.
It learns the wiggles as a required skill.
It does. It thinks the hesitation is part of the solution. It has no way of knowing what's intentional and what's just a human correcting a small error.
You're basically just feeding your policy a diet of noise.
A lot of noise. And the 4th point is a bit more subtle, but it's crucial for actually deploying these things. It's the training and inference mismatch.
Okay, explain that.
So when you train the model offline, it learns to predict these fixed, sort of raw chunks of actions. But when you run the robot for real, the system has all these other things going on, like post-smoothing or temporal ensembling, to make the motion fluid.
So tell the listener quickly, what is temporal ensembling in this context?
It's basically just blending the predicted action chunks together over a short time window. It gets rid of the jitters, makes the motion look smooth and continuous, which you need for a physical robot.
But the policy was never trained on that smoothed output.
Precisely. So there's a disconnect. There's a misalignment between the action the policy thinks it's taking and the action the robot's body actually executes. For a high-precision task, that tiny gap can be the difference between success and failure.
So GRRL is really a comprehensive attempt to solve all 4 of these things.
Yeah, with a very disciplined structure.
Let's get into that structure then. What's the model architecture they're building on? What does the specialist look like under the hood?
Okay, so the base is really powerful. It's a mixture of transformer or MOT architecture.
Right.
It's got a VLA policy, which they call P theta, and a multitask critic, QA. And altogether, it's 5 billion parameters.
Wow, 5 billion. That's a serious model just for lacing a shoe.
It's a statement, right? It says a lot about the complexity needed for real physical dexterity. The VLM backbone is Qwen 2.5 VL3B instruct.
And the policy part, how does it generate the actions?
It uses an action diffusion transformer, or a DIT. It's trained with flow matching, which is just a way of making sure it can generate these smooth sequences of actions efficiently. The whole thing is designed to take in video, language, and the robot's own body state and spit out what to do next.
Okay, let's get into that three-stage pipeline. Stage 1, offline data filtering. This is where they tackle that messy human data problem. So if you can't trust humans to label good and bad moves, how does the robot figure it out for itself?
This is the really clever part. They basically have the robot teach itself using reinforcement learning as a form of self-supervision.
Interesting.
They train that Critic model, Q5, using an offline RL algorithm on all the data, the good runs and the bad runs, and importantly, the reward is super sparse.
Meaning it only gets a reward at the very, very end.
Exactly. A reward of 1 if the shoe is fully laced and 0 otherwise. Nothing in between.
For our listeners, that ability to figure out if you're on the right track when you only get paid at the end, that's like the holy grail of RL.
It is, because in a setup like that, the learned Q value, the critic's prediction, naturally becomes a really good estimate of task progress. If the Q value is going up, you're probably doing the right thing.
And this is where that specific choice of a distributional critic comes in, right? Why was that so important?
Yes, this is the key to making it stable. A standard critic just tries to regress a single, unbounded number. And with sparse rewards, it tends to get wildly optimistic. It suffers from what's called overestimation.
It's like an overconfident planner who thinks everything's going great right up until the moment of total collapse.
That's a perfect analogy. The distributional critic, on the other hand, is forced to predict a full probability distribution, and it's bounded between 0 and 1. It can't just promise an infinite reward. It gives it a much-needed reality check.
So when a human makes a little mistake,
the distributional critic sees it. It registers as a small but noticeable dip in the predicted value, even if the overall task eventually succeeds. And that dip is the signal.
That's the signal to filter, so the logic is just, if the predicted progress drops by more than some threshold, you throw that piece of data out.
That's it. So the final policy is only trained via behavior cloning on this super clean, high-quality data set of actions that consistently make progress. It's a huge step, and the results bear out just how important it is.
Okay, so now we have clean data, but clean data is still expensive data, and you never have enough. So how do they get more out of what they have? This brings us to stage 2, data augmentation.
Yeah, and here they use another really elegant, simple idea. They lean into the robot's own morphological symmetry.
Meaning because it has 2 arms, it can learn from its own mirror image.
Basically, yeah. The Bite Mini V2 has 2 arms, and shoelacing is a very symmetrical task. So they figured, why not exploit that? It's a fantastic way to improve generalization without collecting any new data.
So if the robot learns how to thread the lace into the right eyelet, you can just flip everything, and it now has a perfect example of how to do the left eyelet.
That's the whole idea. They do it across all the modalities. First, the images are flipped horizontally, and they swap the camera feeds from the left and right wrists.
Sure.
Second, the robot's own joint states and actions are mirrored in the world frame. And third, you have to change the language too. Thread the hole on the left becomes thread the hole on the right.
That's incredibly efficient. You're basically doubling your training diversity without a single extra minute of human work.
It's a huge win for generalization. A really great example of exploiting the known physics of your environment.
All right, that brings us to the final, crucial step, stage 3. Online steering. This is where they close that loop and fix the mismatch between the clean, trained actions and the smoothed actions the robot actually performs.
And this is absolutely mandatory if you want millimeter-level precision.
Yeah.
The offline policy just has no concept of that final smoothing step, so you have to fine-tune it online, in the real world.
And they do this with structured exploration in the latent space. Why not just add noise to the joints?
Because for a task this precise, adding random noise to the physical joints is it's a recipe for disaster. You'd almost never succeed by chance. It's incredibly inefficient.
Okay.
So instead, they add a tiny, lightweight network, a noise predictor, right after the main VLM. And its whole job is to learn how to generate these tiny, targeted steering signals that nudge the final action towards a better outcome.
So it's not random noise, it's smart noise. It's a little correction layer that learns to compensate for that smoothing drift.
You got it. And the objective to train it is key. They add a penalty, kind of like a regularization term. It's like a bungee cord that prevents the noise predictor from pulling the policy too far away from the safe behaviors it already learned offline.
And to make this online part work efficiently, They use a special queue function just for this noise space.
They do, yeah. It's distilled from the main Critic, which just makes the whole optimization process much faster and more stable.
And online learning can be famously unstable. How do they keep it on the rails in terms of data?
They use a dual buffer system. A big off-policy buffer that's filled with successful runs from the really good offline model, and then a small on-policy buffer that only has very recent high-quality data. It makes sure the model is only improving on its best behaviors and not getting confused by the old, messy human data.
Okay, let's get to the cold, hard numbers. The incremental gains from each stage really tell the story of the GRRL approach. So walk us through the performance jumps on that shoelacing task.
Right, so let's start with the baseline. This is the GR3 model, just trained with basic behavior cloning on all the raw human data. The success rate was only 45.7%.
Less than a coin toss, which is pretty clear evidence of that noisy data problem.
Absolutely. Then you apply stage 1, just the data filtering.
What does that get you?
That alone boosts the success rate to 61.6%. That's a 16-point jump just from cleaning the data set. I mean, that's the clearest proof you can get that suboptimal data is a massive bottleneck.
Okay, then they add stage 2, the symmetry augmentation.
With the augmentation added, it climbs to 72.7%. So the policy is now generalizing much more robustly across the workspace.
And the final step, the online reinforcement learning.
That's what pushes it over the top. The full GRRL model hits that final, really impressive 83.3% success rate. And if you look at where it improves the most, it's during that critical final step of actually threading the lace through the eyelet.
Let's double-click on that ablation they did for the progress evaluator. You said the distributional critic was key. What happened when they tried other things?
Oh, the failures are so informative. The first alternative was a simple regression baseline, where they just tried to predict time like how far through the task are you.
So like t divided by t.
Exactly. But that method just oversmoothed everything. It was totally insensitive to small but critical mistakes, like the shoelace slipping a tiny bit. It basically gave a false sense of security right up until failure.
I see. And the other alternative, a non-distributional critic.
That one failed for the reason we talked about before. Severe overestimation. Because its output was unbounded, it would just predict a near-perfect outcome from the very beginning. It was way too optimistic.
So only the distributional critic, which is bounded between 0 and 1, was able to properly capture those small dips in progress that signal a mistake.
It was the only one. And it could also identify the positive value of complex moves, which brings us to the actual behaviors the robot learned.
Right. Tell us about the physical system and some of those really impressive high-level things GRRL was able to do.
The robot itself is the Byte Mini V2. It's a mobile manipulator with 2 7-degree of freedom arms and these unique spherical joints in the wrists. They actually upgraded it for this work, increasing the arm strength and making the base smaller so it's more mobile.
And what were the behaviors that really showed it was more than just a high success rate? What showed true robustness?
Well, first, it generalized across different shoe colors and sizes, which is great.
Yeah.
But the proactive behaviors were the most stunning. For example, it learned to do automatic retries. If it missed the eyelet, it would just pull back and try again, without any human help.
But the really amazing one was the re-grasping.
Oh, absolutely. This is where you see true long-term reasoning. In one case, it would grasp the shoelace too far from the tip. It would recognize this was a bad grasp for threading.
And it would then decide to strategically fail in the short term for long-term success?
Yes. It would intentionally drop the shoelace, re-grasp it much closer to the tip where it had better control, and then successfully thread the eyelet.
That is a multi-step, complex, intentional sequence. That's so far beyond simple mimicry. That's actual problem solving.
It is. It also learned to reorient the whole shoe if it was positioned badly. These are the kinds of behaviors that show an agent really understands the constraints of the task.
So GRRL really is this compelling blueprint.
Yeah.
You start with a generalist, you obsess over data quality using RL, you leverage physical symmetries, and then you use more RL to correct for the system's own quirks.
It connects all the dots. And this idea, using distributional critics to get a reliable progress signal from sparse rewards, that's a technique we're seeing pop up more and more. It seems to be a key that unlocks real-world performance.
Now, before we finish, the authors were very upfront about the limitations they ran into.
They were, which is always great to see. They pointed out 2 main issues. The first was behavior drifting during that online RL phase. The policy would sometimes just wander off track.
Any idea why?
They think it might be the noise predictor being a bit too simple, or just that credit assignment is really hard in such a big action space. The second limitation is the lack of a distillation mechanism.
So how to get that specialized knowledge back into the big generalist model?
Exactly. They've made this incredible specialist, but that new knowledge is kind of siloed. The loop isn't fully closed yet to feed that improvement back into the foundational model.
And that really leads to the big final question, I think, for you, the listener, who's digging into this research. If the main bottleneck for dexterous robotics really is just the noise and suboptimality of human data, and that huge performance jump from just filtering the data suggests it is, how far do we push these self-improvement methods like GRRL before we start to question the need for human demonstrations at all? Is the future of robotics about cleaning up our messy data, or is it about abandoning it entirely for perfectly optimized self-generated data?